Welcome to this lecture. This is the final lecture of week 6. In this week, we have studied the weak convergence of random variables through certain kind of convergences of the related distribution functions. We have also connected this with the notion of weak convergence of probability measures on the real line. So, all of these are coming through the specific type of convergences involving the related distribution functions. We have pointed out a list of equivalent conditions for weak convergence of probability measures on the real line, but without proof. We have seen some nice examples of this weak convergence of random variables as well as probability measures. In this lecture, we are going to see some more interesting results which will clarify the material of week 6 better. In particular, we will cover some part of the proof of the equivalent statements that we have made, and the rest of the proof will be left out for later lectures in next week's lectures. Now, we are also going to see certain applications of the convergences that we have discussed. So, without further delay, let us continue the discussion with the lecture notes. All right. So, we start with the question involving random variables for which the distribution is known to be Gaussian, and we are interested in the weak convergence of such sequences of random variables. Recall that if a Gaussian random variable is taken, meaning if the distribution of x is normal with mean mu, which is a real number, and variance sigma squared positive, then the corresponding characteristic function has this known explicit form. So, for all real numbers u, you will get this quantity as the value of the characteristic function. Now, let us look at a sequence of Gaussian random variables such that the nth random variable has the Gaussian distribution with mean mu n and variance sigma n squared. Suppose in addition that the corresponding means converge to mu and the corresponding variances converge to sigma square. Here mu is taken as a real number as pointed out earlier, and sigma square is taken to be positive as also pointed out earlier. Now, let us look at the pointwise limit of the relevant characteristic functions. Here what we observe is that for all real numbers u, let us look at the limit of the nth characteristic function evaluated at u. Then as n goes to infinity, we have to look at the limit of this expression, but then as mu n converges to mu and sigma n squared converges to sigma squared, we immediately have as the limit the characteristic function of x. So, therefore, for all real numbers u, we have pointed out or we have proved the pointwise convergence of the relevant characteristic functions to the characteristic function of the limit random variable x, and this limit is in the sense of weak convergence. This result follows from the Levy's continuity theorem, which we have discussed earlier. Now, let us look at a other case where we consider now that the variances go to 0. So, in the previous case we have assumed that the variances sigma n squared converge to sigma squared some positive quantity, but now let us assume that the variances goes to 0. Then what happens? Then we still continue to assume that the means mu n converge to mu. Now, again look at the pointwise convergence of the corresponding characteristic functions. So, for all real numbers u, the characteristic functions evaluated will give you this expression, and as n goes to infinity, this term will not contribute anymore. So, therefore, in the limit you will just end up with this expression, but this is actually the characteristic function of the degenerate random variable at mu, meaning this random variable y takes the value mu with full probability. So, therefore, what you end up having is that pointwise the characteristic functions of x n converge to the characteristic function of y, which is degenerate at mu. Therefore, you conclude that again by the Levy's continuity theorem, the convergence happens in the weak sense or in the sense of convergence in law or in the sense of convergence in distribution. So, all of these terms are equivalent as we have already pointed out. Then we are having that this sequence of Gaussian random variables, if the variances go to 0, then they converge in the sense of distribution to this degenerate random variable with this law, which is given by Dirac measure supported at mu. All right. So, let us now consider another type of sequences of random variables, where we consider now only degenerate random variables. So, we are now interested in the weak convergence of such sequences of random variables. In fact, in one of our earlier examples, we have already considered something similar. So, there we had considered the degenerate random variables at 1 by n, and we have pointed out that such random variables converge weakly to the degenerate random variable at 0. In particular, we have also pointed out that the convergence of these type of random variables is equivalent to the fact that in terms of the probability measures, their corresponding laws are Dirac measures supported at 1 by n, and therefore, as n goes to infinity, they converge weakly to the Dirac supported at 0. So, this is an equivalent statement in that specific example. What we are going to do is to generalize this situation and look at in general weak convergence of degenerate random variables. So, we again look at two specific cases. So, let us start with this situation, that suppose x n is a sequence of real numbers which is converging to some real number, let us call it x naught. Then note that if we take any bounded and continuous function f defined on the real line, then we immediately have expected value of x n, where x n is degenerate at small x n. This expected value will be f evaluated at x n. This is simply by using the fact that x n is degenerate at small x n. Then the limit of these quantities by the continuity of the function f, we will immediately get it to be f of x. So, this should be f of x naught, this is a minor typo which will be corrected in the lecture notes. But now, this quantity again we just write it in terms of the expected value of f of x, where x is degenerate at small x naught. Therefore, as a consequence, what we have identified is that for all bounded and continuous functions small f real line to real line, we are having this limit of the corresponding expectation, and this is the fact that this is equivalent to the corresponding weak convergence. Therefore, we conclude that the corresponding sequences of probability measures converge in the weak sense, and equivalently the sequence of random variables which is x n's converge in the weak sense to the random variable x naught. So, essentially we are looking at the convergence of the corresponding laws. So, what we have established is that if we are looking at a sequence of real numbers x n, they converge to x naught, then the corresponding degenerate random variable supported at those points converge in the weak sense to the limit random variable which is degenerate at the limit points x naught. Now, we look at the opposite situation. So, we start by assuming that we are having a sequence of degenerate random variables, degenerate at x n for each n, and the limit random variable in the weak sense is degenerate at x naught, and we want to see whether the corresponding sequence of real numbers which is x n has any relation with the point x naught. So, if you again start by assuming that x n's converge to x in the weak sense, now we just go back to the corresponding statement that for all bounded and continuous functions we have this limit. Now, let us simplify this fact. We immediately have, by the evaluation that we have pointed out earlier, that limit of f of small x n, this is now a sequence of real numbers, converge to f of x. This is just evaluating the corresponding expectations. But now, consider as very specific continuous function which we look at as this. So, we have already fixed the point x naught. Therefore, what we do is that we will look at f defined as exponential of minus u minus x naught squared. So, this is now a function which is bounded as well as continuous. Here what happens is that if we now look at the corresponding limit as suggested from this relation, we will immediately get that these terms as n goes to infinity goes to exponential of 0, this is just using the continuity, and that is 1. Therefore, from this we conclude that x n minus x must go to 0, which is equivalent to x n going to x. So, here we have established that if we are having the sequence of real numbers x n converging to x, then the corresponding degenerate random variables converge in the weak sense. If we start with a sequence of degenerate random variables and assume that they converge to another degenerate random variable, then the equivalent condition that we have just ensured is that the corresponding sequence of real numbers, which is actually the corresponding supports of these degenerate random variables, are also going to converge. So, this is giving a nice equivalent criteria for weak convergence of degenerate random variables. All right. So, let us continue. We now start some discussion involving the equivalent statements that we have pointed out earlier in theorem 3. So, we have been so far working with these statements, but without proof. However, just to recall, we have proved the Levy's continuity theorem, which proves two of the statements to be equivalent. One involving the pointwise convergence of the distribution functions at the continuity point of the limit distribution function, and the corresponding pointwise convergence of the characteristic functions. This we have seen in the Levy's continuity theorem. What we do now is that we start by looking at all the other type of statements that are listed as part of theorem 3, and we start checking which of the statements implies the others. So, we go one by one. Let us see. So, we start by looking at this sequence of distribution functions, let us call them f n, and suppose f is some other distribution function. Now, we recall the first two statements from theorem 3. So, the first statement is just the definition anyway, we just write it for the completeness, that we are asking for the pointwise convergence happening, but for the continuity points of the limit distribution function. Now, recall the second statement, we are asking the pointwise convergence to hold, but on a set D which is dense in R. So, a dense set in R simply means that its closure is the whole real line. Now, we want to show here that the two statements are actually equivalent. So, let us start by looking at 1 implies 2. So, we are assuming that as per our definition, the sequence of distribution functions f n converge weakly to the limit distribution function f, meaning at the pointwise convergence holds at the continuity points of the limit distribution function. However, the limit distribution function can have at most countably many jumps, and we know that any distribution function is having discontinuities only through these jumps. Okay. So, these are the only jump points that we need to look at, and these are the only points of discontinuity. So, if there are no discontinuities, we do not have to worry, but if there are any such jump points, they are going to give us these countably many points of discontinuity. Now, let us look at the set D to be the set of continuity points of the limit distribution function. Here D is the complement of a countable set, and hence we conclude that the closure of D must be the whole real line. Therefore, this gives you a explicit set D which is dense in R, and on the set D the pointwise convergence of the distribution functions are true by statement 1. So, therefore, we have proved that 1 implies 2. Now, let us start with the statement 2 and try to prove the statement 1. So, here we are given some dense set, and a priori I have no information whether this dense set is connected with the set of continuity points of the limit distribution function f. Now, what we do is that suppose I take some number x naught, a continuity point of the limit distribution function, then if the function f is continuous at this point, then given any epsilon positive, we just appeal to the definition of continuity and obtain some delta positive, such that we will end up with some neighborhood of the point x naught, where if you take any arbitrary point y, then the function values differ from x naught by this number epsilon over 2. So, now inside this interval, which is a symmetric interval around the point x naught, we are going to choose certain points D1 and D2 from the dense set D, and this we can choose again by the density property. Here we will choose the point D1 between x naught minus delta to x naught and the point D2 between x naught and x naught plus delta. Now, here what happens is that if you now look at the difference of the function values at these 2 points D1 and D2, then by the triangle inequality involving the modulus function, we just add and subtract the terms f of x naught and obtain this estimate. But both of these points D1 and D2 are in the appropriate interval, and therefore, both of these terms are less than epsilon by 2. So, their summation is less than epsilon. Let us denote this relation by star, we will come back to this. Now, we are given by our choice of D1 and D2 that D1 and D2, these are kind of boundaries of the point small x. Stated in another way, x falls between D1 and D2. Now, here if we look at the nth distribution function, this is non decreasing. So, therefore, we will end up with this set of inequalities, and this is true for each value of n. Now, let us look at this set of inequalities. What we do is that we start with the number f of D1. Here, since D1 is a point inside the dense set, we are already given that the pointwise convergence of the limit of the distribution functions holds at this point. So, therefore, this equality holds by the statement 2. But now, let us look at the inequality that f n of D1 is less or equal to f n of x naught, and that is going to lead us to this inequality that the left hand side limit is less or equal to limit inferior of these quantities. However, note that here what we are looking at is that the limit may not exist. A priori we have no idea whether this limit exists or not, but now limit inferior always exists and this is less equal to limit superior. Now, we go back in the other direction. So, this limit superior here we compare with the function values at the point D2. So, here we know that f n of x naught is less or equal to f n of D2. So, therefore, we have this inequality. But now, D2 is a point inside the dense set D, and by again the statement 2 we conclude that this part follows that the limit value here exists and it is if evaluated at D2. Now, here note we go back to our relation star that the difference of the function value of the limit distribution function evaluated at D1 and D2, they differ by at most epsilon. So, therefore, what we immediately conclude is that first of all there is these two limits, limit inferior and limit superior, and therefore, their difference can be at most epsilon. But since epsilon was chosen to be arbitrary, we conclude that these two limits must match, and hence the limit actually exists. So, this is the common value of the limit superior as well as the limit inferior. So, therefore, we have the existence of the limit at the point x naught being a continuity point of the limit distribution function. But here, as in the set of inequalities that we have established, as soon as we know that the limit of f n of x naught exists, we immediately conclude that the limit must be f of x naught. So, this just follows from the set of inequalities that we have described, and we have therefore established that if x naught is a continuity point of the limit distribution function, then the corresponding pointwise convergence holds as n goes to infinity. This completes the proof that 2 implies 1. So, therefore, we have just ensured that the first two statements in theorem 3 are equivalent. But now, here what we want to stress is the fact that we are looking at different kind of dense sets where the corresponding pointwise convergence holds. We have to be careful in the choice of the set where we are asking the pointwise convergence to be held. So, in the definition we are asking for the set to be the set of continuity points of the limit distribution function. In this statement we have seen that we can relax it to be any other dense set, but now we cannot take arbitrary sets and ask for the weak convergence. So, this is a kind of a cautionary example which we establish by certain explicit examples. Let us see. So, here let us look at a sequence of random variables which are taking two values. So, for n equals to 1, 2 and so on, we take the random variable x n which takes the value 0 with probability half and the value minus 1 plus 1 by 2 n with probability half. Now, here we can look at the corresponding distribution functions which can be explicitly written. So, below this number minus 1 plus 1 by 2 n, the distribution function takes the value 0. Then between this range, the distribution function takes the value half. So, there will be a equality here, this will be corrected in the lecture notes. And finally, if x is greater or equal to 0, the distribution function takes the value 1. Now, if you look at the degenerate random variable, degenerate at 0, then we immediately observe that the sequence of distribution functions converge pointwise to the function value f of x, but for the points where x is greater or equal to 0. But we can check separately that this does not imply the weak convergence of x n to x. So, you have to be careful in choosing the set of points where the distribution functions converge to the limit distribution function. So, just to be clear, we will try to work with the continuity points of the limit distribution function. At most, we will relax it to some dense subset of the real line. We now compare some other statements. So, here we recall the 9th and 10th statement as part of theorem 3. So, here in the 9th statement, we are looking at all open sets G in the real line and looking at the sizes of the open set in terms of the given measures. And if the limit inferior of this sequence is greater or equals to measure of G, then this is giving us the 9th statement. Similarly, if we look at all closed sets in the real line, then we again look at the sizes of the closed sets, look at the limit superior of that. If that is less or equal to the measure of f, then this is giving us the 10th statement. What we want to conclude is that 9th and 10th statement are equivalent. So, we start by assuming the 9th statement involving the open sets and we want to prove the statement involving the closed sets. So, here we observe that if we take f to be any closed set, then its complement is an open set and there is a nice relation between the sizes of f and f complement because the given measures are taken to be probability measures. Therefore, mu n of f must be 1 minus mu n of f complement, mu of f must be 1 minus mu of f complement. Now, we go through certain interesting calculations. We start by looking at limit superior of mu n of f and we want to show that it is less or equal to mu of f. But now, use the relation in terms of the complement. So, we write first this is 1 minus mu n of f complement, but this is a nice property of the limit superior that these can be rewritten in terms of 1 minus the limit inferior of mu n of f complement. But for open sets, I am assuming that the limit inferior has the appropriate bound and that is going to give us the other side of the inequality that we want and therefore, this is less or equal to at the end measure of f. And therefore, we have established the 10th statement. If we want to prove that the 10th statement involving closed sets implies the 9th statement involving open sets, we just have to argue in a similar manner that any open set is actually the complement of any closed set and therefore, from the 10th statement we can get the 9th statement. So, therefore, 9th and 10th statements are equivalent. So, in the subsequent discussions, if we are given one of 9th or the 10th statements, we can assume any of the two, we can in fact use both of the statements and this is something that we are going to use in our next argument. So, here we first recall some other list of statements that was mentioned in theorem 3. So, we recall the statements 11th and 12th. So, here in the 11th statement we are looking at all mu continuity sets in the real line. So, here mu continuity set simply means that the boundary has measure 0 in terms of the limit measure and here I want the limit to hold. And the 12th statement is involving some special type of intervals left open right closed where the boundaries which is the 2 points a and b that set has measure 0 under the limit measure. We want to show that 9th or the 10th statement, which are now equivalent as we have already established, implies the 11th statement, and on its own the 11th statement implies the 12th statement. So, let us see one by one. So, we first assume that the 9th statement holds. As already pointed out, we can now assume that it is also the 10th statement is true. So, we want to show that for a mu continuity set, the appropriate limits are true. So, we start with any arbitrary mu continuity set. Now, look at two other sets, which is the A interior and A closure. So, A closure by definition is a closed set, A interior by definition is an open set. Now, here we appeal to the 9th and the 10th statement and get certain inequalities. So, let us see one by one. So, we start with measure of the mu continuity set, but since the boundary is 0, this is same as the measure of the A interior. Now, A interior is open, we can appeal to the 9th statement to say that this is less or equal to this limit inferior, but A interior is contained in A. So, therefore, we end up with this next inequality, that the first limit inferior involving the A interiors is less or equal to limit inferior involving the original set A, but limit inferior of this sequence is less or equal to limit superior of this sequence. Again, we observe that A is contained in A closure. So, therefore, we go in turn to the limit superior involving the closure of the set. Now, here we apply the 10th statement, which is equivalent to the 9th, but this is involving the closed sets, and therefore, this is upper bounded by this number. But as the boundary of the set A is 0, we immediately also have that this is matching with the measure of A. So, we started with measure of A on the left hand side, and we have obtained a set of inequalities and ended up with measure of A again on the right hand side. Therefore, all the inequalities in this calculation must be equalities, and in particular this inequality must be an exact equality. So, therefore, this will first of all establish that the limit of mu n of A must exist, because the limit superior and limit inferior match. But now, this limit exists, and therefore, this must be equal to measure of A, because all the inequalities now collapse to equalities. So, therefore, the statement 11 follows. So, we now assume that the statement 11 holds, meaning for mu continuity sets the appropriate limit is true, and we want to show it for these type of intervals that a similar result is true. But now, we are assuming that the measure of the boundary points of this interval are giving you 0. So, therefore, this set, which is left open right closed, has the property that its boundary has measure 0. So, therefore, this A, which is an interval, is a mu continuity set. So, therefore, by the statement 11 we essentially reduce it to statement 12, and therefore, statement 12 now follows that as long as the left open right closed interval is a mu continuity set, and we know the statement for all mu continuity sets. So, statement 12 follows from statement 11. So, let us take stock of our situation. So, in theorem 3 we have stated a list of 14 conditions. So, we have already discussed some of the implications and equivalences. So, let us make a list. So, we have seen that the statement 1, which is the pointwise convergence of the distribution functions, but at the continuity points of the limit distribution function, is equivalent to the limit involving measures of sets of the type minus infinity to x closed, where measure of the singleton x is 0. But you remember, this is exactly connecting to the corresponding distribution function. So, this is the correspondence between probability measures and the corresponding distribution function, and therefore, the statement 13, which involves the corresponding measures involving such half infinite intervals and their measures, will be exactly equivalent to the statement 1, because this is just rewriting the distribution function in terms of the measure of such half infinite intervals. So, therefore, 1 and 13 are just restatements of each other. But now let us recall the other statements that we have proved. So, in remark 13, which we have discussed in this lecture, we have shown 1 and 2 are equivalent. In remark 14, we have shown that 9 and the 10th statement are equivalent. In remark 15, we have shown that the equivalent statements 9th or 10th implies the 11th, which in turn implies the 12th statement. And also in an earlier discussion, we have discussed the Levy's continuity theorem, which shows the convergence of the distribution functions which we are talking about is equivalent to the pointwise convergence of the corresponding characteristic functions. So, this was part of the Levy's continuity theorem, but here we have to keep in mind that we have used the fact that 1 implies 3, which we are yet to prove. So, we will prove 1 implies 3 and all the remaining implications in subsequent lecture, which will be discussed in the next week's lectures. So, in this week we have introduced the concept of weak convergence of random variables, of probability measures and of distribution functions, and we have seen certain interesting examples of such convergences. We have seen that convergence in probability implies the weak convergence, but here the important thing is that weak convergence can be defined for random variables which may be defined on different probability spaces. We have also discussed some of the equivalences between the statements that we have pointed out in theorem 3, and we are going to continue proving the rest of the equivalences in the next week lectures. We stop here. Thank you.